for chapter 7. All right, chapter 7, like I said, the key one is exercise 7C. So no matter what I say, please do not spend time on A and B, just do C, okay? I know it says A, B, C there because it carries all the skills of A and B. Do C, all right? C is the key one. You spend a bit of time to understand what I'm going to teach you today, then D and E will become much easier. Okay, D and E is the application, the applying, and C is the theory. So this is what you're going to copy for now, okay? So all the things I taught you about moving left, right, up, down, thin, wide, and then flipping and all that, it actually comes from this first exercise, 7C, the theory. So let's take it like this. For every coordinate that you can think in a graph, so a graph has many, many infinite coordinates, it can be transformed, which means manipulated or changed, by either BODMAS, add, subtract, multiply, divide. That's what we're doing to the numbers, okay? Those have names for them. So when you add, subtract, we call that translation. You're moving left and right, or up and down. Multiplying is what you see when we say dilation, which makes it thinner or wider. So it's like a stretch. That's how I normally explain it to my students. So I say it's either stretch horizontally or stretch vertically, or compression. Versus, and then the thing is you can also multiply by negative numbers, which makes it a flip, okay? This table here summarizes A, B, and C in terms of transformations you need to understand. So here, we take as an example, let's say a coordinate, x, y. Okay, so this represents the original coordinates. And I'll do a visual aspect on the slide just so you can see here. But let's say this is your y-axis, this is your x-axis. Let's say I picked this point. That's where xy is. So that's my point right there. If I want to move, okay, to the right by 1. So I'm going to fill in this spot here. So fill in this spot and say right by 1. Okay? On the x-axis, if you look at this coordinate, if I asked you where is it now, you would say wherever this is, I'm going to add 1 across, right? So it would have moved across by 1. That means it will now land at x plus 1. But the y value does not change because all I did was I shifted to the right by 1. So what you see is this will move to the right by 1 and it looks like this. This is your new coordinate and that will be at x plus 1, but the y value is still the same. Does that make sense so far on a visual aspect? Yeah? So this is called translation of 1 unit to, actually I should write this down because it sounds fancy. Back in the past you actually had to memorize this sentence, but now you can say to the right by 1. But back then they used to say translation of 1 unit in the positive direction of the x-axis. It's very long. But you can see the components, translation is just moving. 1 unit, so which unit? Is it left or is it right? 1 unit, if you want to say to the right, it's positive direction of the x-axis. If it's up, then it's positive direction of the y-axis. If it's down, it's negative direction of the y-axis. Yeah, so this used to be the language that you need to apply in your exams. Nowadays, you don't have to. You can write move to the right by 1, but the examiners will not say move to the right by 1. The examiners will use this language. So you need to know how to interpret it. Okay, notes are up here if you need. All right, so by that theory, if you're looking at what I've got over here for you then, if x, which is your x-axis, to move to the right by 1, I added 1 to the x values, then what do you think minus 1 tells me then? What's minus 1 tell me? Left. Okay, so this one must mean left. Then what about this one now? So notice its y values, you add 1. So if you visualize that picture again that I've drawn for you, the y values, if I add 1 to it, it's actually shifting the coordinate up. That's right. It's going up. So each coordinate y value, if you add 1 to it, it shifts up. So then the x value stays the same, but the y values move up by 1. Okay? So this one is up, and the other one must then be down. So far, so good? This is called mapping notation, by the way. So if I were to apply it, this is what a mapping notation looks like. So in exams and your SAC so far will look something like this. It'll say original XY coordinate will map. That's what the arrow means. Will map means it transforms to, and depending on whatever your transformation is, notice that in the column I used X dash Y dash. That is the notation so that you know it went from the original X to the new X, from the original Y to the new Y. Usually I say old X, new Y, old X, new X, old Y, new Y. Okay? It helps you, especially in next exercise. I'll teach you how to use a technique to identify. That's why you need to know the difference between the two. Okay, so far I've only taught you when you're moving left and right. You know how I say let things equal to 0? Let that bracket equal to 0? That was me cheating. I was actually meant to tell you to let it equal to X prime or Y prime. But I don't tell you that because I'm scared to confuse you. So I just tell you let it equal to 0. Okay, but that's for next session, that you understand why I told you to do that. Okay? Let's go. So that's pretty much exercise 7A. 7A was translations, up, down, left, right. And your goal in exercise 7C is to read mapping notation. If you're able to read from this to that, so meaning these ones, that is the first skill of exercise 7A. Cool? Let's read the next one. 7B. 7B is a bit different now. B, arguably, to me, is the trickiest. And you'll find out soon later in 7D when I teach you a technique. 7B is the trickiest to do. Okay? But in terms of reading it, it's not too hard. So here, when I put a 3y, okay, so what this is saying is your original xy coordinate, I'm going to multiply just the y coordinate by a factor of 3, meaning I'm tripling it. Okay, so let's have a think. Here's my values again, and I'm going to change all of this. Just delete that. Let's give it a number so you can visualize what's happening here. So I put this down. Let's say I picked the values 1, 1. So you got the coordinates 1, 1, right? If I now said I'm changing 1, 1, where for every xy coordinate, I'm now going to multiply the y value by 3. What would the new coordinate be now? So following this mapping notation, for every xy coordinate, it will become x and then 3y. What would the new one be? 1, 3, because the x doesn't change. I'm not multiplying the x, so the x stays the same. Still 1, but 3, I'm multiplying to the y value. So if y is 1, this becomes 3. So what's happening here is when I do a multiplication, the coordinate is still 1, but in fact, it's gone up by a factor of 3. This is my new coordinate. This is what we call a stretch. It's not moving. We're not taking a spot and we're moving per unit. We're doubling, tripling, quadrupling, yeah, for every single coordinate that you can think in a graph. So like a quadratic graph, the picture that you can see, imagine every single coordinate gets tripled. Then that's what a stretch looks like. Okay, so this is called a dilation. So exercise 7B, we say, when you put a 3 on a y, can you see how you're multiplying the y values? And watch my hand movement. Can you see how my hand's sort of moving up and down? This is going to help you remember the language. Language, dilate by a factor of. Factor of means what are you multiplying by? So I'm multiplying by a factor of 3. Now the key word is this one. So the word from. From means you're moving away from a certain point. Now if I'm moving this, which axis am I moving away from? X. So the language is from the x-axis. And students confuse this because you're multiplying the y values, but it's from the x-axis. And that's why they get confused. Okay? The other language might make it easier is that you say something like, sometimes they say dilation of factor 3 in the. Okay, so in the, then this case, instead of word from, then this one would be in the y-axis. So there's actually two ways of describing it. That's why dilation gets a bit tricky when you're interpreting it. Okay, but dilation is simply just means a stretch. So if you didn't understand what I was saying there, copy this one down. All I'm saying, that line there, dilate by a factor of 3 from the x-axis, just means stretch vertically by 3 times. That's what it actually means. Okay, so when we say dilate, it means stretch. Factor of 3 is the 3 times, but from the x-axis, because you're multiplying the y values, that's actually a vertical stretch. Okay, that's what it actually is. So you always look at the coordinates and you ask yourself, am I multiplying to the y's or am I multiplying to the x? Because if I'm multiplying y's, it's a vertical stretch. If I'm multiplying x, then it's a horizontal stretch. Okay, so let's have a look at the next one. This one is 3 multiplying to the x, so this would be a dilation of factor 3 from the, which axis is this now? Yeah, so think about, these are your x-axis. Okay, but if I'm tripling it, I'm moving this way. So I'm tripling all the x values. Where my hand's moving, I'm moving away from the y-axis. So here you would then say away from the y-axis. If that's hard for you to remember, just think of it as if you're multiplying to the x values, it is a stretch, but a horizontal stretch. And the reason why this is a bit harder to see over time is because a lot of students don't normally see a horizontal stretch in a graph. The best graphs that you can actually see a horizontal stretch is an exponential graph and maybe a surd graph. Okay, so I'll show you a transformation so you can see what I mean by horizontal and vertical stretch. Okay, so here we go. Let's go Desmos. I'm going to put on Desmos. Let's take an exponential graph, which you haven't learnt yet, but let's do 2 to the power of x. This is what an exponential graph looks like, right? The key point I want you to look at is this one, 0, 1, the y-intercept. Watch what happens here. So I haven't taught you how to make a transformation equation yet. That's for our next lesson. I want to show you what a horizontal stretch is and what a vertical stretch looks like. So if I want to stretch all the y values, yeah, you said 3 times the y values, right? This is what y is. Y equals 2 to the x. So if I times it by 3, meaning if I said y equals 3 times 2 to the x, see what I'm doing there? I'm saying 3 times 2 to the x, but 2 to the x is y. That's tripling every y value. What you see is 0, 1. If I'm tripling the y value, so just take that coordinate, that will transform to 0, but 1, you're going to multiply that by 3. It should actually be at 0, 3. You see that? That one, that point, that just one singular point has been tripled to that point there. Can you see that? So this is now 0, 3. Because I'm saying that right there is my dilation of factor 3 from the x-axis. It's moving. So you can see the graph, every single one of these points, no matter which one you pick, it's tripled. Everything's tripled, and it gives you that illusion that's going up. Versus if I did a horizontal stretch. So if I zoom out, that's what a vertical stretch looks like. It gets a bit taller. But watch what happens when I do a horizontal stretch now. Okay? So a horizontal stretch means I'm going to multiply the x values. So a horizontal stretch, which you might get confused here, but it's okay. Just trust me. This is going to be a factor of 3, okay? So 2 to the x times, whoops, let me change that. There we go. I know it looks like a divide 3. Next lesson, you understand why it looks like this. But look at what I've done here. 0, 1, can you see I've actually stretched it horizontally. The black line is a horizontal stretch. This is a vertical stretch. They're both factor of 3s. So if I zoom out, you see how it's stretched out? This one's away from the y-axis. You see that? All right? This is what determines a stretch horizontally. Whatever you do to the y, see I'm affecting the x here. This one I'm affecting the function, which is the y value. So every time you affect the y's, it's vertical stretch. Every time you affect the x, it's a horizontal stretch. Okay? Don't get too bogged down on this one. I was trying to give you a visual idea of what it looks like. Okay? All right, that's 7B. So 7B, what is your goal for today? It's not to do what I just did. It is to read this. So if I give you a mapping notation, what I want you to be able to do is that you should be able to look at the equation and say, yep, dilation, factor 3 from, and you have to get this one correct. If it's affecting the y, moving up and down, that's away from the x-axis. If it's affecting the x, it's moving away from the y-axis. I need you to be able to interpret that. That's 7A, 7B. Make sense so far? All right. Last one. C just combines all of them, but 7B has dilation, and it also has what we call a reflection. Reflection is also known as a flip. Okay, that's where you see it gets flipped upside down, or it can be flipped horizontally as well. But here, when they say a negative y, when they say you put a negative on the y value, let's visualize what's happening. Let's go back to this graph again. If I put a negative on the y, okay, so let's read the mapping notation. I'm going to switch it all again. If I gave you x, y, and I said it's going to map to a negative on the y value. So if I gave you the point 1, 1, where would it end up? So if this is my mapping notation, I say whatever x, y coordinate you have, we are going to make it x, negative y. What would this be? Where's the new coordinate going to end up? 1 minus 1. Very good, because I'm saying keep the x, just put a negative on the y. So keep the x, put a negative on the y. So 1 minus 1 looks like this. This is where 1 is, and minus 1 is down here, right? So that's where minus 1 is. What kind of flip is this? Is this a vertical flip, or is it a horizontal flip? Vertical. So when it's a vertical flip, you're clearly jumping over the x-axis. Yeah? So the language we say reflect in the x-axis, because it's like there's a mirror that's reflecting in the x-axis, because the mirror is on the x-axis. Okay? Whatever's here is symmetrically over there. So hence, when you put a negative y, if there's a negative y here, we say reflection in the x-axis. And all this means is flip vertically. Okay. And then your last one, obviously if you put a negative x, you can kind of picture it. 1, 1 becomes negative 1, 1. So hence this now is reflection in the y-axis, and that just means flip horizontally. Now, if you put all this together, this is all the theory that you need to know, and all I needed you to understand was to be able to read it. So in exercise 7A, B, C, what you're doing is they're going to give you a bunch of this. Your job is to be able to read what is that asking you to do. Okay. Next lesson, I'll teach you how to apply that knowledge. But first, you have to be able to read. This is called a sequence of transformation. Let's do an example now. Now that you got the notes there, so these are my notes, let's do an example together. Let's read this one. I want you to describe the sequence of transformation, because that's what it is. Sequence of transformations. So this is an example of exercise 7C. This is what they'll do. They'll give you a bunch of transformations, and your job is to be able to read what this means. Read one transformation that you can see. Let's go with Sion. Name me something that you can see. Yeah, what's the negative x mean? Yes, but I want the proper language. Look at your notes. Oh, you didn't get the notes. Oh my God. I'll pick someone else. Sorry? Oh, you were right. Notice I wrote here BODMAS, because BODMAS you do your multiplication division first before addition subtraction. When you put in your order, sequence of transformations, they call it Dr. T. Okay, so DRT for Dr. T. You have to put in that order. So yes, Sion just talked about the negative x. That negative on the x, if you looked at our notes just now, negative x represents reflect in the y-axis, which means flip horizontally. Okay? So here we can then say, all right, I've got a reflection in the y-axis. Great. That's correct. We've got one of the transformations. Give me another one. Can I please have, let's go with the muffin. Give me another one that you can see. What else can you read from this transformation? Sorry? Left by 1. Very good. So this here, this -1, so all the x values are minusing by 1. So when you're -1, means you're moving to the left 1. Very good. So that's a translation. So under translation, I'm going to say left 1. Very good. We've got left 1. Give me another one. Let's go with Ishan. What do you see? Beautiful. That is a multiplication. That's 2 times the y coordinates. So it's dilation, okay, but you're multiplying y. So think about the hand movement again. Every y value, you're doubling it. So it is dilation of factor 2 from which axis? X. Very good. Okay, so here I want you to get in the practice of writing it. It's dilation of factor 2 from the x-axis. And that just means vertical stretch. I'm doing a vertical stretch there. Okay, so that has a vertical stretch. And what's your last transformation that you can see right now? Let's go with Milena. What do you see? Yeah. That +3 is on the y coordinates. So if you add 3 to it, it goes up by 3. That is exercise 7C. How's that feel so far? So 7C was combining A, B, and C together. I just did it all in one go. Yeah, so you're reading mapping notation. That's the first skill. If you can't read it correctly, you can't transform it correctly. So you must learn that skill first. Okay? Hardest one is dilation, especially when we get to the next exercise. Okay, so copy that down. Copy that down. And then once you're ready, flip over the page because we're going to do a couple more examples and trying to get you a bit more used to the language. Okay, I want you to use the language correctly. If you're wondering what that therefore is, it's Dr. T, just for dilation, reflection, translation, if you're curious. All right, here we go. Let's flip over to the next page. Let's look at this one now. All right, looks like I'm introing to the next exercise, but let's transform the language into a mapping notation first. Okay, so I'm giving you a hint for those who want to go ahead. This will now teach you a bit of 7D, but if you can transform this to this, then I can teach you how to go from this to a new equation. Okay, so watch this. Actually, not watch this yet, but let's transform. What does dilated by a factor of 2 from the y-axis represent? Very good. So dilate means times 2, to which values y-axis. So think about the y-axis, it's from. When you do that in your hand movements on your head, it's clearly multiplying to the x-axis. Yeah? So it has to be 2 times x because it's a horizontal stretch. Good. Reflected in the x-axis. Ooh, close. It's minus y because, remember, reflection in the x-axis, if this is the x-axis, then that means that's where the mirror is. That means the point goes from this point to this point. So it's symmetrical that way. If it was in the y-axis, the mirror is this way. And it jumps from left to right. That's then a flip. Yeah, so in this case, it should be negative on the y values, right? So this one should be a negative y. That's what reflected in the x-axis is. You'll get used to this. Next one. Last one should be much easier. Translated by 3 units in the positive direction of the x-axis. What am I saying? Plus? To which one? X or y? X, very good, because it says direction of the x-axis. I'm going to the positive directions, moving to the right. So here, plus 3. How's that feel? Because that's 7C. Okay, so if you're unsure what I just said, use my notes. And if you want to practice 7A, B, C, I recommend just doing C. This is all you're doing. So you're practicing to read the notation. 7D is the application. So now that you know how to read a mapping notation, how do you go from this to the new equation? So this is your graph. This is a root x graph. This is what a root x graph looks like. Like that, right? If I want you to do exactly what you just told me, stretch it vertically, so double it vertically, then I want you to move it to the right, and then I want you to flip it upside down. We know what it kind of roughly looks like, but what's the equation? How do you type that in an equation? So I'm going to teach you a technique to get there. Okay? This technique is good when you get to year 12, when you're moving complex equations to complex. Later on, you can just kind of read the equation. Yeah? So here we go. This is the technique. So starting from here, I do want you to copy the notes because this is going to be the essential part of chapter 7. Here we go. Remember I told you this x dash, y dash? This is your original x, original y. This is your new x. That's your new y. Okay, so make sure to copy that down. This is new x, new y. Within it, that's old x, old y. So that means you can say new x, to get to the new x coordinate, it must be the result of doubling the old x plus 3. Okay, so that's my equation, the first one. The equation for this second transformation is the new y coordinate is the result of timesing -1 to the old y. So far, so good? Okay, so that's all I'm doing. I'm just rewriting what I'm seeing. So this new x is dependent on that. This new y is dependent on that. Yeah? Now, see how your original equation is original x, original y? You want a new equation. So if you want a new equation, well, you need to know, well, what is new x dash and what is new y dash? What is the coordinates equal to, right? You have to rearrange this to replace it because right now that's in original y. So what I'm going to do is I'm going to rearrange this now. I'm going to say -3 on both sides. That gives me x dash -3 is equal to 2x, and then divide both sides by 2. Original x is equivalent to x dash -3 divided by 2, right? Now to help you also see, to be able to read later on, I want you to split this fraction into 2 fractions, not just one. See how they share a denominator of 2? I can split it up and write it as x is x dash over 2 minus 3 on 2. Yeah, I'm just separating them. The reason why I do that is because it makes it clearer when you put it back into the equation. You can see what's being multiplied to the x dash and what is moving up and down. Yeah. Whereas this one, if I just divide both sides by -1, then I will now have negative y dash equals original y. So I've got original y, I've got original x. So far the technique seems pretty simple. This is x, it's original y. Here's the technique. You want a new equation. So you need to replace that old y, since now you know what old y equals to. Old y is equal to negative y dash. I can substitute this back in. So I can say, all right, let's substitute that to that, because old y equals old y, right? Old x is equal to old x. So whatever is here, I'm going to replace that with this. Whatever is here, I'm going to replace it with this. That gives me y dash, negative y dash, is equal to the square root of x dash on 2 minus 3 on 2. Is anyone confused with what I just did there? Because this is pretty much the technique. Okay, that's it. This is what you're practicing in 7D. So I'm already showing you 7C's here. This is 7D. This is the kind of skill you want to just keep practicing, because eventually you don't need to do this step. You should be able to tell me the new equation. Okay? Part of what I taught you as well, you know how I told you let it equal to 0? This is where I cheated. When I taught you guys how to move left and right, instead of telling you it's equal to x, I actually told you guys to let it equal to 0, so you're doing this bit. See how I did that? minus 3. That's what you guys were doing. That's what I was trying to teach you to do. But that's for later on. I'll contrast it back and you'll understand. Yeah? Anyways, so what is the new equation? Here we go. Normally you have just y by itself. So I'm going to times both sides by a negative. Times both sides by a negative. Times this by negative 1. Negatives and negative cancels out. Then I go to times this by negative 1. And so you get the new equation. Y dash is equal to, I'm just going to rub this out so it doesn't confuse you. Y dash is equal to the negative root x dash on 2 minus 3 on 2. Okay? So if I now show you on Desmos, you will see exactly what we just described. It should be a stretch. If you type this on Desmos, it should be double vertical stretch. Should move to the right by 3. Is it left or right? I can't remember now. 3, yeah. 3 to the right, and it should flip upside down. Let's see if it's true. So here we go. Let's go to Desmos. I'll delete them all. Y equals square root of x. Here we go. That's our function. Let's make it look a bit nicer. There we go. We're going to type the new one that we just figured out. So it's y equals negative root of x over 2. And I think it was minus 3 over 2, yeah? So, can you see? Definitely moved to the right by 3. It's definitely flipped as well, because that's what we asked. And we said it had to be a double stretch. Okay, so double stretch from which axis was it again? It was double in the x-axis. Okay, sorry, it says from the y-axis, but all the x values get stretched horizontally. Yeah? Can you see how the graph looks like a horizontal stretch? It's thinner. It's getting pulled out that way. So the blue graph looks flatter compared to the red graph. That right there is an illustration of what we're doing there. You see that? So what you practice 7D, if you're comfortable, you can work on 7D by working to get to this point. But otherwise, I want you to work on 7C first. 7C just trains you to do this bit. That's what you need first. Okay, so you need this bit first. 7D, I just showed you the technique. If you want to have a go yourself, you can try this one. Okay, you can determine the sequence transformations. But I'm going to leave this for next lesson, okay? Don't do this one yet. I want you to work on 7C. Work on 7C, get used to reading the transformation. And then, if you're comfortable, try 7D, pick up a few questions, see if you can get this. If you like one to challenge yourself, just to see how much you understand, here's one I'm going to make up, so it's relevant. You know how I taught you up, down, left, right with quadratics? Well then, let's do this one. What if I gave you... Oh, my pen died. Let's go. I'm going to draw it on the board. For those who want to have a go,